Okay, good morning everyone. I hope you can see my screen. So let me quickly summarize what we have done in the last few classes. So in the last few classes, we have been exploring machine learning, and within machine learning, we have been exploring supervised classification problems. We looked at several algorithms like k-nearest neighbors, naive Bayes, decision trees, random forest, and we have seen the logic behind them. We have also seen how our validation methodology works. How do we know our algorithm is training well? So there are three basic ways of doing that. We saw using the three-way split, that is dividing our data into train, test, and validation. We saw also that that is a inferior method, a generally more superior method, especially when data is less, is doing something called as cross-validation, where we divide our data into multiple parts and we train over multiple iterations. And in each iteration, we use one as a validation set and the remaining as training set and so on. And thirdly, we saw something called a stratified cross-validation, which is the same concept as cross-validation. The only difference is now that when we divide our folds, we are ensuring that each fold has an equal distribution of the target class. We also saw several evaluation metrics for classification. We saw something called as accuracy. We saw precision, recall, F1 score, F beta score. And we saw that these methods or these evaluation metrics, they help us to see how good or how bad we are doing. Today, we are trying to consolidate everything into the one algorithm into the one data set that we have been exploring earlier. We looked at something called as the Titanic machine learning from disaster dataset, in which we have already processed our data and prepared our data, which is now ready to be fed into a machine learning algorithm. Okay, so I will just skip this part, go till the end to where we have reached. Let me come here. Okay, this is where we had finished in our previous classes. Let me run my kernel till this point. Okay, so it should take a few seconds to evaluate everything and reach to this point. And oh, I think it is stuck in between. Okay, let me do things from here manually. Okay, so I'll quickly summarize. So you wear your sandals and come. I'll quickly summarize what we have done here. Is the Titanic training dataset had several columns, and we are trying to predict the passenger survived status, that is whether the passenger has survived or not. And for this surviving, we are looking at several features like, okay, just give me 1 second. Okay, sorry, my baby was making some noise. Yes, I was summarizing our data set. So our data set has something called as the survived column, which we want to predict. And we want to predict that based on several different features like passenger class, sex, age, fare, title, where did they embark from, what is the family size. And we did that once we have processed our data. So processed our data means we have taken care of missing values. We have taken object types, that is string type data, and converted that into numbers. We have converted different ranges of data into a discretized range. We have done binning. And for categorical data, we have done something called as one-hot encoding. So post that, our data is now ready so that it can be fed to a machine learning algorithm. Okay, we have processed the same for training and we have processed the same for test. Now we are moving ahead. So the algorithms that we saw, like k nearest neighbor, decision tree classifier, random forest, naive Bayes, or support vector classifiers, these algorithms are available from a package called as scikit-learn. Now, since we know the math, of course, you can go ahead and you can write your own code that does the task. But in most cases, that is not required unless you have reached an advanced stage where you realize that you need to make certain modifications with your algorithm to work well with your data set. But I think that that's at a much later stage. For now, we can always depend upon scikit-learn, which is a wonderful package tested and tried by so many people and used over multiple years and continuously updating. This package is now available for us to use. So you see the first command that I'm calling here. I'm calling from scikit-learn, that is the package scikit-learn. There's a module called as neighbors, and from that I'm importing a function called as k neighbors classifier, which is also your knn, the same thing. Okay. Then from scikit-learn's tree module, I'm downloading or importing a package called as decision tree classifier. From sklearn, scikit-learn's ensemble method, I'm calling random forest classifier. From naive scikit-learn naive Bayes, calling Gaussian naive Bayes, Gaussian NB. And from sklearn.svm, I'm importing SVC. So with these importing or with these packages, now we can feed our data, our X to our model and try to learn what is the underneath, what is the pattern that we are seeing underneath. Okay. Okay. So additionally, from scikit-learn's model selection method, I'm calling kfold. So kfold is the cross validation helper. What it will do is it will divide our data set into multiple parts, and for each part we'll have a validation set and training set, and it will manage those concepts. Okay. We also call a function called as cross validation score, which will help us to see what is the cross validation score over multiple sets. So you see here kfold, I'm importing, or I'm addressing the value of n splits, that is the number of splits that I want to be 5. So 5 is the standard number of splits that we want to do with our data. If you have more data, you can also go up to 10 splits. So here I'm doing 5 splits. I've kept shuffle as true, and I've kept some random state. So the idea of a random state is when I want to run this file multiple times, I end up with similar answers. That's just the reason for that. And from this object, from this constructor of kfold, we create an object k underscore fold. So let me execute this. Yes. Now that's the important part. At this point, we are trying to see what is if I feed this data to knn, how it will work out. So I'm calling k neighbors classifier. And at this point, almost randomly, I've selected that I will choose the first or the closest 13 neighbors. And based on the closest 13 neighbors, we will define a classifier. And based on that, we will evaluate our data and see how it works out. So this first line, k neighbors classifier, n neighbors equal to 13, creates a classifier. Okay, I define the scoring to be accuracy. So since in my case, the distribution between survived and not survived is not very far, okay, then I can use accuracy as a measure. Otherwise, we could use different methods like F1 score, F beta score, and so on. So presently, we use accuracy as a method for scoring, and I call the cross val score. So this is the cross validation scoring function, to which we provide the classifier. We provide what is the trained data. We provide the target. So this is our X, capital X. This is our small y. We provide CV, which is cross validation. In fact, here I should, instead of 5, I should be providing k underscore fold, where I'm saying that my cross validation should happen because of this k fold method. Number of jobs is how many parallel processes do I want to run. So for me, 1 is fine for this data. And I keep my scoring as this variable scoring. So when we execute this code, we see that we get 5 numbers. Okay, so we get 5 numbers because of five uh, cross validation folds that we had divided our model into. We divided the model into 5 parts, and on each part we are getting a validation score. Okay, so what has happened in the background is out of those 5 parts, 4 parts were taken. Our model was trained on those 4 parts, and then we evaluated our model using the fifth part. And since we already know the answer of the fifth part, we are then comparing how many of them are right. What is the accuracy? So on our first set, it gave us an accuracy of 80.44%. On the next, we got 82.58, 84.26, 79.77, and 82.58. So we have five cross-validation scores. Now, it would be better if we could combine this into getting one answer. That is what I do here next. I do something called as take the mean of all these five values, and we end up with 81.93. So what we see is KNN helped us to get a score of 81.93. Now, if you remember long back, we had created a simple model of all the women are saved and all the men have died, and that model was around 70-75% right. We see that by using all the other features, the KNN model has allowed us to go to some higher level of accuracy. Okay, somewhere near 81.9. Let us try now. Is this the best score that we can get? No, we have not yet tried fine tuning. But at this point, we are just exploring how can we run through multiple algorithms. So we saw that running through k nearest neighbors was such an easy deal. We did not have to write anything. Just by writing k nearest classifier and calling the cross-validation score, we were able to train the model. Going ahead, if you want to see decision tree classifier, so I take decision tree classifier, just this one line gets changed, I get a new classifier. I keep the scoring as same, I keep the cross-validation as same. Now when we execute this, we can see that these are our mean, or these are our independent scores for each of the five splits, and our mean score comes to around 80.25. So by the default parameters, decision tree gives us 80%, 80.25, whereas KNN gives us 81.93. Let's check random forest. Okay, random forest gives us 80.36. Going ahead, naive Bayes, we get naive Bayes as 79.46. And finally, SVM gives us 82.72. Okay, so in the default scoring algorithm, we have seen that 82.72. Okay, just 1 second. Okay, so we see support vector machine gives us 82.72 accuracy. Going ahead, so this was our base accuracies depending upon the different algorithms that we have seen. Going ahead, we will try to do some fine tuning. So this is the next topic that we had seen, where we see that there are several hyperparameters within each algorithm. That means there are several places that we can tweak, or we can ask the algorithm to choose different values and check out. Okay. So within fine tuning, what we'll do is we'll try all of these different parameters and allow scikit-learn's grid search method to find out which of these works the best for us. Okay. So here from scikit-learn.model selection, I import grid search CV and randomized search CV. Okay. Looking at this code here, I'm calling a variable called as param_grid, which is a dictionary which defines all of these hyperparameters that we want to change. So k nearest classifier, k neighbors classifier, has these hyperparameters like number of neighbors. So here I choose range of 5 to 30. What this basically translates to is I will be trying 5, 6, 7, 8, 9, 10 till 29 neighbors, and for all of these neighbors I want to see what the score is. Then my weights can be either uniform or distance based. So we choose uniform or distance. Algorithm can be ball tree, KD tree, brute. The three options we try. And P is when I'm using a distance, what is the order of it? So P of 1 is Manhattan, P of 2 is Euclidean, P of 3 is Minkowski, and so on. So of course, you will not know what these parameters are. So to get an idea of what are the parameters in this model, we can simply do a help. So I'll show you how this works out. I can write help of k neighbors classifier. And when I execute this, I can see a help routine. And within the help routine, first, even at this point, I can see what are the different parameters that they have used. So n neighbors, weights, algorithm, leaf size, P2, what is this, metric, uh, metric param, and so on. So these are the different parameters you could play around with. If you want to know more about these parameters, we go down and we see these parameters, and it explains to us, at least in simple terms, what this means. So n neighbors is the number of neighbors to use by default for example k neighbor queries. Okay, so here the default value is 5. That means if you don't define how many neighbors, it will take a default neighbors of 5. In our case, then we can modify it. Okay, you can check out weights and you can see what is the meaning of weights. You can check out algorithm, you can see what are the different options we have. So based on this help file, we can decide what options we want to play around for the parameter grid. So when I execute this, so this defines the grid I want to search in. This is the copy of the classifier. And now we call the method grid search CV, which is grid search cross validation, to which we provide first the algorithm KNN. We provide the grid in which it has to search. We say, what is the k-fold? What is the cross validation? So for cross validation, we'll be using the k-fold variable that divides our data into 5 spots. We use scoring as accuracy. Verbose is basically when it is running, how many, to what level of detail do I want to see the output? So when I keep verbose as to, that is the max level of detail. So as we run this algorithm, we can see the different steps it is doing. Number of jobs as -1. So by defining -1, I'm saying that choose as many parallel processes as possible. Okay, the maximum number of parallel processes as possible. So that is what it means by -1. And by doing that, we create an object called as grid search. Finally, we can fit that model by calling the grid search.fit function, to which we provide x, our data, our processed data, and target, which is our small y. Okay. Now, when I execute this, see what happens. So it says that because of these options, we have 450 candidates that it has to test. Okay, so there are 450 models that we'll be testing. Each of those models will be testing with 5 folds, which gives us a total training of 2,250 words. Now, if you have to do this manually, of course, it is not impossible. Thankfully, this algorithm helps us to try all of these different options. After trying all of these different options, it took us around 14.3 seconds to evaluate. Okay. After running them out, we can see that what is the best it has chosen. So if I run this grid search.best parameters, I can see that it has chosen from algorithm ball tree is the best. It chose 10 neighbors, Manhattan distance, and weights as uniform. So after trying through all the options, this was the combination that gave us our best score. Okay. If you want to get our best estimator, you can directly write best estimator and say, okay, this is the best estimator that we have. What is the best score? Our best score is 82.71%. Okay. So k nearest neighbors along with fine tuning. So without fine tuning, it was giving us 81.93. And now with fine tuning, it is giving us a score of 82.71%. Okay. Going ahead, we can try for different algorithms. So let us try for the one that gave us the best score. So in our earlier exploration, we found SVM giving us the best score. So if we try running a fine tuning with SVM, if we do an help on SVM, the different parameters that you can change is one called as C. So C is a level of the level of margin that we arrange that helps us to define something called as regularization. Then we have the kernel. So we have linear, polynomial, RBF and sigmoid kernels. We can define degree and so on. At this point, we'll just choose to change C and kernel. So we try these different options for C, 0.01, 0.03, 0.1, 0.31, this. So this is one of the hints that I found from a famous professor from Stanford University. His name is Andrew Ng. And if you're learning machine learning, you should know this guy's name. He's kind of a must go-to person in terms of doing the basics of machine learning. So what he suggests is when you're trying out with grid search, you should try in multiples of 3. So when I go with the first one, 0.01, multiple of 3 will take me to 0.03. Multiple of 3 would take me to 0.09. So I rounded out to 0.1. Then 3 times is 0.3, 3 times is 1, 3, 10, 30, and so on. So I'm trying over a big range of values for C. For kernel, I take all the options possible, that is linear, polynomial, RBF, and sigmoid. And everything else in this code remains same. We take SVC, take a copy of that to, okay, here okay, let me first change to grid search CV. Okay, and I'll remove this parameter. So we'll try with grid search CV, and now when I execute this, okay, this is parameter. Okay, so here we have 5 folds, 32 candidates, total 160 fits. And after that, we find our best parameters as C of 0.01 and a kernel of polynomial. Our best score is 83.16, which is the best score we have seen so far. That is 83%, right? We can also, from grid search CV, extract the different validation scores. Okay, so if I take grid search.cv results, I get CV results here, and I extract something called as mean score and what is the parameters that we tried for, and I run this loop. I can see these are the different scores we got for different combinations. So when we chose a C of 0.01 with kernel linear, we got 78.9%, and here it gives us all the different runs that we executed. So all the different, how many runs? 32. All the 32 combinations it gives us here. Okay. Okay. Once we have the best estimator, we can train it once more with all of the data. So cross validation misses out one data set, splits one split. But when we train with all of the data, then we have probably a better result. Once we have trained with all of our model, we can check its score, and we get a score of 83.61. And like this, we could try for different options. Let us try even decision tree and see what we get. So after trying decision tree, we can see that it gives us a score of 88.4, which is much higher than what we got by SVC. Okay. Going ahead, once we have trained our model, what we want to do is now predict for our unknown cases, predict for our test data. So let me see what went wrong here. Okay, so here we want grid search.test estimator. So copy this, paste it here. Then train. Okay. Okay. It seems to say that our input contains some missing values. We had tested it, but maybe it must have passed. Let me do a test.head, and we'll do test.isNull.sum. And we have a missing value for fair that has passed out. So for now, let me just fill it with the mean. So I can say new test is equal to test.fill NA with test.mean. And that's it. And now if we run this, okay, missing values has been filled. Let us try with we're trying it with our best estimator, that is our decision tree estimator, and we can then get our submissions. Okay. So what we have done is we have predicted for a new key data set, that is for a test data set. We have fit the model with train. We have dropped passenger ID. With our test data, we are testing something called as we have predicted for a prediction, and we have stored it into a CSV file, which we are reading here. And this is what our model says. Our model says that passengers 18, 892, 893, and all these guys have not survived, whereas 896 has survived. So let me see the first top 10. And we can see that our model is giving out some prediction. Now, how good or bad our prediction is, for the test data set, we cannot know, because this data that we had, it was not labeled for test. Okay. But I hope you got an understanding of how we are training the model. it is actually very simple. Once we understand the basics, we are just calling methods from scikit-learn's module, and with those scikit-learn module methods, we are testing our model and training our model and seeing how they work out. Okay. What I want to do next is I want to look at one more example, and I'll probably introduce you to a very good website that you can use for machine learning. And I hope some of you guys who are already exposed may know of this website called as Kaggle, but let me show you once again. So Kaggle is this wonderful online place where we can many data scientists come together and they practice different algorithms, getting data, participate in different competitions, participate in forums and asking doubts and questions and so on. Okay, so on this Kaggle platform, I have uploaded a competition called as heart disease prediction. In fact, let me in the chat window, let me paste the link to this competition so that you guys can have access to it and participate in it at this. Okay, so I am just pasting in the group this link. Okay, and what this link will allow you is to come to this competition and participate in this competition. You just have to go to the link, and here in my screen where it shows my submission, you should see a link called as join the competition. Once you join the competition, you will have access to data and notebooks and so on. So in this data, that is the heart disease prediction, let me quickly talk about what the problem is, and then we'll look at how to get to a sample solution to this problem. So this problem is basically from medical database, where we have around 14 attributes, and these 14 attributes are given here. They are ID, age, sex, CP, which stands for chest pain type, rest BPS, which stands for T-rest BPS, which stands for resting blood pressure. We have call, which stands for cholesterol level, FBS, which stands for fasting blood sugar. We have rest ECG, which is resting electrocardiographic results, THALAC, which is maximum heart rate achieved, EXANG, which is exercise-induced angina, old peak is the ST depression induced by exercise relative to rest, slope has 3 values, 0, 1, 2, CA, which is the number of major cells, 0 to 3 colored by fluoroscopy, and THAL, which is 0 for normal, 1 for fixed defect, 2 for reversible defect. And finally, the condition variable, which says that given all of this data, does someone have heart disease or not? So a value of 0 says that they have heart disease. A value of 1 says that they don't have heart disease. Okay. So this is what our data looks like. There are around 13 attributes and 1 target class. Okay. And like this, we have 2 sets, train and test. So train has number of examples and test has number of examples. Our task for machine learning is this, that using the train data, we'll try to learn, or we try to train the machine learning algorithm so that with our test, so that we can predict for our test, so that for our test data, we can predict our answer and we can see how good our model is doing. Okay. So once you go and join this competition, if you go to this tab called as notebooks, you can see that a notebook called as starter model. So this is my attempt or my help in getting you started in this competition. Of course, you can update this competition and change things according to what you like, apply and see what score you get. Okay. So this score that I put up gave this simple model gives us a score of 81%. Let me go to this model and show you how this data would look like. Okay. So this is the notebook. Now this notebook is running in Kaggle's environment. Just like we saw that Google Colab is an online platform, a cloud platform where you can run your Jupyter notebook kind of structure, where you can do Python programming at Google's expense. Here we are doing it at Kaggle's expense. Okay, so Kaggle is another platform here where I can directly load my notebook and start coding here. The advantage is that since you're running on a cloud network, it doesn't matter what is the configuration of your system. Your system may have low RAM, low GPU, no problem. You can work at this online platform. The only thing that you need to ensure is you have a good internet connection so that you can run your commands and see the output. So we'll be doing the following steps within our hard disease prediction, and these are the standard steps that I would suggest any beginner to start with in their data science project. Once you gain some experience, you can see you can skip a few, you can mix and match, you can do several things. But at this point, the first things that we want to do with our data is we want to do something called as data exploration, data visualization, pre-processing, feature engineering, modeling, and finally validation, evaluation, and testing. Okay. Going ahead, we first load all of our, we load our packages. So here I'm calling NumPy, Pandas, Matplotlib, Seaborn. These are our standard packages that we'll use. I load the data. So when I load the data, I get a train file and a test file. I load the train file into a data frame called as dftrain, and I load the test file into dftest. Okay. When we look at dftrain.head, we can see that these are our, this is what the data looks like. We have ID, age, sex, CP, T-REST, BPS, cholesterol, FBS, REST ECG, THALAC, exang, old peak, slope, CA, THAL, and these are our features, whereas our target variable is here given by the target column. Similar to seeing the data frame, train data frame, we can look at our test data frame, and we can see that we have all the same columns except for the target variable. Okay. Going ahead, now we start our phase of data exploration and visualization. The first thing that you can do with the data is we can do at dftrain.describe. And what the describe function does is it helps us to see our basic statistics on each of our features. Okay, so you can check, let's say for age here, we can see that the mean age of our participants is 54.34. Okay. In fact, let's start with ID. Okay, let's start with ID. When you do a count of ID, we can see there are 212 different objects, which tells us that our data, at least our trained data, consists of 212 different items. Okay. Of these 212 different items, we can see our age is a mean age of 54. We have a standard deviation of 8. Our minimum age is 29 and our maximum age is 74. So our participants are ranged between 29 to 74 age with a mean of 54 and an average or standard deviation of 8.84. We can see gender. So we see a mean of 0.71. That means 71% of our patients are male. The remaining are female. And we can see the standard deviation. We can see min max. So since sex is just a Boolean value, that is 0 or 1, it doesn't make sense to look at the 25 percentile, 50 percentile, and so on. So you can see all of these features. Oh, I have not disabled annotation. Just give me a moment. This should be fine, and let me erase this. Okay. Okay, so here the describe gives us basic understanding of how our features are distributed and what are their values. Okay. Now there are certain things that we need to ask of our data. First thing we would ask is, are there any missing values? So let me check dftrain.isnull.sum.sum, and we see 0, which basically suggests that our train set does not have any missing values. What about the test set? We see the test set also does not have any missing values. So that is one less problem for our data pre-processing. We don't have to deal with missing values. So here we say, great, no missing values. Let's go ahead. Let us see if our target class is balanced or not. So if I look at the target class and I do a value counts on it, I can see that there are 116 examples of 1. So remember, 1 means no disease and 0 means disease. Okay. So we have 116 examples of people not having heart disease and 96 examples of people having heart disease. Now, I would say that this is very close to being balanced. So we would not worry too much about it. Going ahead, we want to know what are the categorical features. Okay. Now, if you go through the list above, that is the description of the list above, description of this data. Okay. If you go to the description of this data, you can identify what are the categorical variables. So the categorical variables here are sex, CP, FPS, rest ECG, exang, slope, CA, and thal. And what I do is I take all of these features and I load them into a list called as categorical features. Okay, load that into a list called as categorical features. Now we could also go ahead and do something called as count plot. That means for each of these categorical features, I want to know what is the distribution. Okay, so this is an extra cell. Let me delete it out. Let me execute this part. Okay, so what I'm doing is I have run a loop over all of the categorical features, and for each of those features, I'm doing a count plot. Okay, what is a count plot? A count plot is something that helps us to see how the data is distributed over this column. Okay, so if I look at one of these charts, we can see that the variable sex, it defines male or female. So 1 is male, 0 is female, and we can see over this category how the data is distributed. So target 0 means people having disease. Target 1 means people not having disease. So looking at this data, can you quickly tell me, in our data, do we have more males or more females? Okay, just to ensure that you guys are listening to me. Okay. In our data, do we have more males or do we have more females? So what do we have more? Males? Okay, excellent. Okay. Additionally, which gender, that is male or female, which gender has more chances of having a heart disease? Remember, 0 means heart disease and 1 means no heart disease. So which gender has more chance of having heart disease? Okay. So I just see the old answer as males, but since the new answer is also male, it is difficult to tell if you guys understood or not. Let me show you here. Okay. So here we see sex 1, which is male. We have more. So our total here, male is more than female. So that was right. Secondly, we are asking who has more chances of getting heart disease. So if you see 0 means heart disease, 0 is this blue color. In males, the blue color is the bar chart of this blue color is taller than the bar chart of this orange color. That means in males, we have more chances of getting heart disease. Whereas when you look at for females, we can see the bar for blue is much smaller than the bar for orange, which says that females here, at least in this data set, the females are more unlikely to have heart disease. Similarly, we have done the same for each of the different categorical features. Okay, so in a normal scenario, I would want that as a data scientist, you would go over each of these charts and get an idea of what is happening, so that you can look at the features and see which features are important or not. But since here we are falling short of time, I would skip this step and go ahead to the next part. Okay. Since we asked the question, what are the categorical features? The next question that is very logical to ask is, what are the numerical features and how are they distributed? So what I do is I use a very simple idea. I create a set of all the columns, and from the set of all the columns, I subtract all the set of categorical features and ID and target. So when we do that, we end up with all numerical features. So we have these numerical features: age, thalak, rest, T-rest, BPS, cholesterol, old peak. And what I want to do is I want to see the distribution plot of all of these values. So we will execute this, and we can see a distribution plot for all of our data. Okay. So here, when we look at age, thalak, rest, let us maybe analyze one of these. Let us look at age. Okay. So when you look at age, okay, let me zoom on this distribution. When you look at age, the blue one describes the age or the distribution of age of people who are more likely to have heart disease. And the red one, the orange one, gives us the distribution of people who are less likely to have heart disease. Okay. So looking at this graph, do you find something interesting? Or do you find Okay, let me ask you a question that will be easier for a chat environment. Okay, the question is, do uh, are younger people more likely to have heart disease, or are older people more likely to have heart disease? So younger or older for more likely to have heart disease. Okay, older. Great. Yes, obviously older. True. So obviously older. I would assume you're going with the idea that what we understand about the data, that is, older people are more likely. But we are also at least what we say satisfied that our data represents this idea also. Okay, our data represents the idea that people who are older have higher heart disease, as can be seen with this blue group. We can also pinpoint which is the age group that has the highest heart disease. Okay, you see these two bars, these high bars, and they are at around the age of 60. So we would say that people who are around the age of 60 are more likely to have heart disease than people who are around the age of 70 or 80. Okay, that is another observation that we can make from our distribution. Okay. Similarly, we have the same distribution for all of our features, like T-rest BPS, cholesterol, and world peak. If you observe something like T-rest BPS, I would say that this feature is not important for us. And the reason I would say this feature is not important is because the distribution of data for the, the people with heart disease and for the people not having heart disease, both are similar. And since both are similar, they may not be very beneficial for us, at least in terms of our machine learning algorithm, to distribute or to help in classification. Okay. So wherever they have a difference, that data is more important. Okay. Okay. Looking at numerical, categorical, and numerical features, we are going to the next part. We are asking, how are the features correlated? Now, if you remember when we were doing pandas, I explained what correlation means. Correlation is basically between. So here we are looking at between the different features and even between the target variables. That is, if one increases, is the other one increases or not? Okay. So again, it is better to show you a diagram and then discuss on that. Let me. This is something that is not required. Let me remove this out. Yes. Okay. So what we're doing is we are creating a heat map. Okay. Let me quickly show you what the code is. So in the code, what we have done is we have taken sns.heatmap that tells draw a heat map. Heat map is basically this matrix of rows and columns in which we have different colors, and the colors describe something. For this heat map, we are saying fill it with this part. What is this part? This is saying df train, take all the numerical features and the target variable and do a correlation over it. So we do a correlation over all the numerical features, and we will use that as input for our heat map. We are saying annotation is equal to true. When we say annotation is equal to true, you see the text in between 0.24, 0.24, 0.25, that will be written. We then provide the format of this annotation, which is saying 0.2f. That means write the annotations correct up to 2 decimal places. We are saying use a color map of diverging palette. That means that decides what color will be printed here. We want C bar as false, so let me put color bar as true so that we can see the color bar, and we keep square. Okay. So when I execute this, C, we get this plot, and it's very interesting to read this plot. Okay, so let us look at the target variable. Okay, and let me see if you get some few questions right. Okay, so if I look at the target variable, can you tell me which is the most positively correlated feature with the target variable? Most positively correlated feature. Okay, I am not seeing many answers come in. Okay, some people are saying age, talent, okay, talent, okay. Okay, so I have some mixed answers. Let me explain this idiot. Okay, if I zoom this further, you can see the target variable, and you can see the most positively correlated is this number 0.46. Okay, that is the most positive value. Of course, we have the value 1 here, and you should ignore all of these diagonal elements. Why? Because correlation with its own self will always be 1. So that is not important for us. Apart from that, we have just one positive feature, which is thalak, and it is having the value of 0.46. What this basically means is as thalak increases, target also increases. Okay. When you look at other variables like what is the most negatively correlated, so you can see the most negatively correlated is old peak. That means as old peak increases, target reduces. Okay. So this helps us to find out if how features are correlated and are they important or not. So comparing between a negative correlation of cholesterol and old peak, we would know that old peak is much more important than cholesterol because cholesterol changes very slowly as compared to old peak. Okay. So with that, we have seen how the heat map looks like. Let us go ahead and we will prepare our data. So I take all the categorical features and numerical features and put that into a variable called as xtrain. Take all the target variables and put that into a variable called as ytrain. If we look at the shape of xtrain and ytrain, we can see that we have 212 examples, 13 rows, 212 examples and 13 columns for our train and 212 examples for our output. Okay. Here I am also introducing something more ideal. That is, instead of preparing our data individually, we can use something called as pipelines. And pipelines are very beneficial, especially when you want to work on more data in a more concise fashion and do several steps in between. Okay, so I'll not talk too much about it. Let me go ahead. So here we are creating something called as a numerical pipeline. And in this numerical pipeline, we'll be taking all the numerical features. So the first step is select all the numerical features. And the second step is scale all the numerical features. So scaling is a part of data preprocessing. We call this a normalization. That means putting all of our data into a similar, a similar range. So when we use something called a standard scaler, all of our data will have a mean of 0 and a standard deviation of 1. So we do this only for the numerical features. For categorical features, at this point, we're not doing anything. Okay. So we have two pipelines, numerical pipeline, categorical pipeline. Numerical pipeline has 2 steps, select the data, scale the data. Categorical pipeline has 1 step, just select the data. Okay. So we create both of these pipelines. Okay. Going ahead, if I fit transform with numerical pipeline, I can see that now I have an answer of, I get an output of 212 rows and 5 columns. Why 5 columns? Because we just have 5 numerical features. Similarly, when we do a categorical pipeline.fit transform, we can see 8 features because there are 8 categorical features. We can also combine both of these pipelines into one group. That is, here we have numerical pipeline and categorical pipeline, and I've attached that into something called as feature union, which is the full pipeline. Okay. So now when I take my data and I transform it using the full pipeline, I can see that all the 13 features get transformed. So what does it mean by this transformation? It means that the numerical features are scaled and the categorical features, we have done nothing to them. Okay. So with this, I can prepare my data. That is my X prepare train. And once we have our prepared data, we can then feed it to our machine learning models and see how good or bad they do. Okay. So in this case, I'm using algorithms like logistic regression, k-neighborist classifier, Gaussian based, decision tree classifier, support vector classifier, random forest classifier, and gradient boosting classifier. Okay. So more algorithms that we have studied, but you would see that it doesn't matter what algorithms we are using, because or at this point, it doesn't make any difference to us because we are not implementing anything. We're just loading it from scikit-learn and we are trying out the model. Whatever gives us the better score, we can stop at that. Okay. Also, I'm calling from scikit-learn's metric module something called as accuracy score and classification report. Now, when we look at logistic regression, take a copy of logistic regression in lr.clf and fit the data, that is X prepared train and Y train, predict it on X prepared train, we can get something called as our training prediction, and we can check how good or bad our model was. So when we try logistic regression and we look at the classification report, we can see that we got an accuracy of 87%. We have a precision of 92% for 0, that is for disease. For people having disease, we are having a precision of 92%, whereas a recall of just 79%. For people not having disease, we have a precision of 84% and a recall of 94%. In this case, since our data is more or less distributed, we can settle with this one number, 87%, and just look at this number over multiple different algorithms. Here we see that 87% looks good, but unless we do cross-validation, we will not know how good this is. Okay, so we import our cross-validation modules. We'll divide into 5 splits. So all of this is exactly what we did earlier, and now we are running through cross-validation score. We can see that these are our different scores. Our mean score comes out to be 83.4. So here we had got 87 just with training accuracy, but now with our cross-validation, we get a more stable result of 83.4% and a standard deviation of 0.5%. Okay. Let us directly fine-tune our models. So to fine-tune our models, we'll call the grid search cross-validation method. And for logistic regression, these are the several options that we can try. I'm trying out these options of C, these options for max iteration. We load our logistic regression, call the grid search method, call the fit method, print the best parameters, get the best estimator into something called as logistic regression CLF, evaluate the score for this best estimator, again fit our model with the data, predict it for our data, evaluate our score, and load all of this into a data frame. Okay, so there are several things that we are doing here. Basic is we are trying different models, we are testing the models, and we are storing the training accuracy and validation accuracy for this data. So when I execute this, we can see there are 105 fits, and after running through all of the models, it just took it 0.9 seconds to finish. We found a training accuracy of 87% and a validation accuracy of 83%. Okay, going ahead, will be just trying different examples for different models. So here, doing the same thing for KLN, trying all of these options. We can see that it hardly takes us a second, and we have our KLN accuracy of 85% for train and 83% for validation. We try for naive Bayes. We can see naive Bayes gives us 84 and 83 for decision tree. Okay, so here there are many options. We are having 3,250 different options. So let us see how long it takes. It takes 7.7 seconds for all of these models, and we get training accuracy of 82, whereas a bad validation of just 71%. Let us try with SVM. It gives us accuracy of 84%. Let's try a random forest. Okay, so random forest obviously takes more time because you understand, right? Random forest, for each iteration, there will be multiple trees. So this is one layer above decision trees. So, okay, we have to do 540. You see here. Yes, we have to do 540, and for just 46, it has taken 9 seconds. I'll allow it to run, and we'll continue our discussion ahead. So once we have run through all of these models, we will get some idea of what is the best performing model. We have to choose the one which gives us the best validation accuracy. Once we have chosen the one with the best validation accuracy, we can use it for our deployment. That is, take the test, pass it through the full pipeline, use the best model, and once we have the best model, create the prediction. And then within Kaggle's environment, we can submit that prediction and see what score we have got. Okay, let me see, has this finished? No, this is still running. Nonetheless, I have given you the link of this competition. So if you go to that link, you will now have access to this notebook. And through this notebook, you can play yourself. Okay, you can make a copy of it. You can run the several models. You can create your own prediction, and for that you can submit it again on Kaggle, and we can see how good or bad you did. So with random forest, we have seen that we are getting a training accuracy of 1 and a validation accuracy of 79%, which basically means that our model is heavily overfit. So even with random forest, our model is overfit. Basically now we would have to play around with certain options and see which gives us the best score. So in this case, SVM gives us the best score. I will quickly find the prediction using SVM. Okay, so SVM gives us this prediction, and as I told you, earlier only I've submitted this prediction, and I've gotten a score of around 81%. Okay, but you can play around with the data. I hope we can do many things with this data set, and get some better predictions or get some better score. Okay, so with this, we'll stop here. And what we have finished now is we have finished our exploration on classification algorithms. From the next class, we will look at regression, and we'll see how we can look at a different kind of problem statement where our target label is continuous in nature. Okay. With this, we'll stop here today. Thank you so much for joining. Okay, Neerja ma'am, I'll exit for now. Okay. Bye. Thank you. Okay. Thank you so much. See you tomorrow. Bye bye.